Two worlds, nearly 4 billion miles apart, nothing alike in size, temperature, or history, and yet, buried inside the light reflecting off both of them, sat the exact same fingerprint. Not a rough similarity, not something explainable by coincidence. A single, precise wavelength of light, absorbed in almost identical fashion by two surfaces that should have had no chemical reason to match each other at all. Researchers checked every reference they had, every published catalog of known molecules, every laboratory spectrum ever recorded for exactly this purpose. None of it lined up. Whatever was absorbing light at that specific wavelength had never been formally identified anywhere in the solar system or on any planet orbiting any other star ever studied. This is the real story of what James Webb just found on Titan and the signal that still doesn't match anything on the books. In a study posted online in June 2026, a team of researchers led by planetary scientist B. Bézard compared infrared observations of Saturn's largest moon, Titan, against separate James Webb observations of Pluto, nearly 4 times farther from the Sun. Using two of Webb's most sensitive instruments, NIR-SPEC and MIRI, the team had deliberately focused on a narrow slice of the infrared spectrum between roughly 4.9 and 5.4 micrometers, a window largely untouched by the atmospheric haze that usually makes it difficult to study either world's actual surface. Inside that narrow window, both worlds showed something neither was supposed to share, a distinct dip in reflected light, centered at almost exactly 5.11 micrometers, where nothing should have been absorbing anything at all. 5.11 micrometers. That's the specific wavelength of infrared light where both Titan and Pluto are quietly swallowing more light than any known compound should allow, a signature so precise that researchers could line the two spectra up directly on top of each other and watch the same dip appear in both. 6 to 7%. That's roughly how much of the light Titan's surface absorbs at that exact wavelength, a small but unmistakable dip once researchers isolated it from the surrounding spectrum. 3 times stronger. That's roughly how much more pronounced the same absorption feature is on Pluto, suggesting whatever material is responsible sits in far greater abundance on the dwarf planet's surface than on Titan's. 4 billion miles. That's roughly how far apart Titan and Pluto sit from each other in the outer solar system, one orbiting Saturn at about 9.5 times Earth's distance from the Sun, the other drifting through the Kuiper Belt nearly 4 times farther out still, in a region of space cold enough that ordinary rock and ice behave more like frozen gases than solid ground. To understand why a single missing wavelength mattered enough to warrant its own published study, it helps to understand just how well scientists already believed they knew both of these worlds. Titan is not a minor object in the outer solar system. Larger than the planet Mercury, it is the only place beyond Earth known to have stable liquid pooling on its surface, vast lakes and seas, fed by rain and rivers, sitting under skies that produce genuine clouds and weather. None of it involves water. Titan's surface is far too cold for that, hovering around 290 degrees below 0 Fahrenheit. Instead, its lakes and rivers are filled with liquid methane and ethane, natural gases that behave, at those temperatures, the way water behaves on Earth. Much of that picture came from NASA's Cassini spacecraft, which orbited Saturn for 13 years, and the European Space Agency's Huygens probe, which rode along with it and landed directly on Titan's surface in January 2005, sending back images of a rocky, fog-shrouded landscape carved by rivers of liquid hydrocarbons. Between the two missions, scientists mapped Titan's lakes, tracked its seasons, and sampled its thick nitrogen and methane atmosphere in extraordinary detail. Cassini's cameras couldn't see through Titan's thick orange haze in visible light. So much of that mapping relied on radar, bouncing microwave signals off the surface and timing their return to build a picture of the terrain hidden underneath the clouds. That approach revealed seas larger than some of the Great Lakes on Earth, dune fields stretching across the Moon's equatorial regions, and a shoreline geography eerily similar to Earth's own, carved not by water but by hydrocarbons that behave the same way at temperatures nearly 300 degrees colder. It was, by any measure, one of the most thoroughly mapped worlds in the outer solar system by the time Cassini's mission finally ended in 2017, deliberately plunged into Saturn's own atmosphere to avoid any risk of contaminating Titan with material from Earth. By the time James Webb turned its own instruments toward Titan for the first time, in the fall of 2022, astronomers already had one of the most detailed pictures of any moon in the solar system. What Webb added was a level of chemical precision no previous mission had been able to achieve from a distance. In 2023, using infrared filters tuned to different altitudes in Titan's atmosphere, Webb and the ground-based Keck Observatory in Hawaii tracked methane clouds rising and shifting shape over a period of days, offering the clearest evidence yet of active weather patterns on the moon's northern hemisphere. Later studies used Webb's data to trace a missing chemical step in how ethane forms in Titan's atmosphere, filling in a gap in the moon's chemistry that had puzzled researchers for years. That missing step involved a molecule called a methyl radical, an unstable fragment produced when sunlight breaks apart methane high in Titan's atmosphere. Scientists had long suspected methyl radicals played some role in eventually producing ethane, one of the two hydrocarbons filling Titan's lakes, but no instrument had ever been sensitive enough to actually detect them directly above the moon. Webb's infrared spectrometer finally caught the signature, confirming a chemical pathway researchers had only been able to guess at for decades. It was the kind of finding that rarely makes international headlines on its own, quietly closing a gap in scientific understanding rather than opening a new mystery. A separate study published in Nature Astronomy in 2025 and combining Webb's observations with additional data from the Keck Observatory extended that picture further, characterizing Titan's atmosphere during its late northern summer season and tracking subtle shifts in temperature and haze as the moon's decades-long season slowly turned. Titan takes nearly 30 Earth years to complete a single orbit of the Sun, meaning a single Titan season lasts roughly as long as a human childhood, and each new observation adds another small piece to a climate cycle far too slow for any one mission to fully capture on its own. None of those earlier results, however, had turned up anything resembling the June 2026 finding. This was not a new detail added to an already familiar picture. It was a signal with no known explanation at all. Anomaly 1. An absorption line appearing on Titan's surface that matched no molecule in any published planetary spectrum. Anomaly 2. The exact same absorption line, in the exact same narrow wavelength, appearing independently on Pluto, a world 4 times farther from the Sun, roughly half Titan's size, and by most measures, a completely different kind of object. The location of the signal made it harder to explain away as some kind of atmospheric artifact. Researchers concluded the absorption was most likely originating from material sitting directly on the surface of both worlds, rather than from gas in either Moon's or dwarf planet's atmosphere. That distinction mattered. An atmospheric signal might have been explained by some shared, well-understood gas drifting between similar temperature zones. A shared surface material on two bodies this different pointed toward something else. An ice or an organic compound capable of forming under a surprisingly wide range of conditions, cold enough for Pluto and just warm enough, relatively speaking, for Titan. Confirming that the signal came from the surface rather than the atmosphere required its own careful process of elimination. Both Titan and Pluto have real atmospheres, thin in Pluto's case and thick in Titan's, and any absorption feature could, in principle, come from gas molecules floating somewhere above the ground rather than material sitting directly on it. Researchers compared the shape and behavior of the signal against known atmospheric absorption patterns for methane and nitrogen, the dominant gases on both worlds, and found the feature didn't match the way gas phase absorption typically behaves at that altitude and pressure. Surface ice, by contrast, produces a broader, smoother kind of absorption dip, consistent with what Webb had actually recorded. It was an indirect argument built on how the light behaved rather than a direct image of the surface itself, but it was consistent enough across both worlds that the research team felt confident stating it as their conclusion. There was a second twist buried inside Titan's data specifically. The absorption signal wasn't spread evenly across the Moon's surface. It showed up more strongly on Titan's trailing hemisphere, the side that faces away from the direction of its orbit around Saturn, than on its leading hemisphere, which faces forward. That kind of lopsided pattern isn't unheard of in the outer solar system. Other icy moons show similar hemisphere-by-hemisphere differences, often tied to how charged particles trapped in a planet's magnetic field bombard one side of an orbiting moon more than the other. Whatever produces Titan's mystery signal, in other words, may not be spread evenly across the moon at all, but concentrated by forces linked to its orbit around Saturn itself. Researchers proposed several possible candidates for what the material might be, careful to note that none had been confirmed. One possibility involved a form of benzene mixed with another, still unidentified compound. Others pointed toward frozen acetylene or a form of ketene ice, both plausible outer solar system ices capable of forming under extreme cold. None of the candidates matched the observed signal precisely enough to be called an answer. All of them remained, for now, educated guesses. Each of those candidate molecules has its own reason for making the shortlist. Benzene has already been confirmed in trace amounts in Titan's atmosphere, produced when sunlight breaks apart methane, and the resulting fragments recombine into more complex ring-shaped molecules, so finding a benzene-related compound on the surface would fit naturally into chemistry researchers already understood was happening overhead. Acetylene, a simple hydrocarbon gas on Earth, freezes solid at the temperatures found on both Titan and Pluto, and has long been suspected of coating parts of the outer solar system's coldest surfaces in a thin, glassy ice. Ketane, a reactive molecule containing carbon, hydrogen, and oxygen, is less commonly discussed in outer solar system chemistry, but laboratory experiments simulating extreme cold have shown it can form and persist far more readily than researchers once assumed. None of the three, on its own, perfectly reproduced the exact shape and depth of the signal Webb recorded, which is precisely why the study's authors stopped short of declaring any of them the answer. In the weeks after the study circulated online, some corners of public discussion reached for a much larger explanation. An unidentified compound, present on two different worlds, tied to Titan's already well-known status as a laboratory for the kind of organic chemistry thought to precede life, was an easy detail to stretch into something more dramatic, hints of biology, or at least prebiotic chemistry more advanced than anything confirmed so far. It made for an exciting thread to pull on. It was not, according to the researchers behind the study, where the evidence actually pointed. Unidentified spectral features are not new in planetary science, and they are rarely evidence of anything exotic once properly investigated. Astronomers have chased down mystery absorption lines before, on comets, on icy moons, and in the rings of giant planets, and in nearly every case the eventual answer turned out to be an unusual but entirely ordinary compound, some specific ice or organic molecule that simply hadn't been catalogued in enough detail to be recognized on sight. The honest, most likely explanation for Titan and Pluto's shared signal is some form of complex ice or hydrocarbon chemistry, produced by cold, patient processes that have had billions of years to work, not a marker of biology or anything resembling it. One well-known precedent involves Europa, Jupiter's icy moon, where scientists spent years puzzling over reddish-brown streaks crossing its frozen surface before eventually tracing the coloring to a combination of sulfur compounds delivered in part by charged particles from Jupiter's own radiation belts, and salts altered by exposure to that same harsh environment. The explanation, once confirmed, turned out to be almost mundane compared to some of the more dramatic guesses that circulated while the mystery remained open. Titan and Pluto's shared signal may well follow the same pattern: years of careful investigation, several false leads, and an eventual answer rooted in ordinary chemistry rather than anything requiring a rewrite of what scientists thought was possible in the outer solar system. That doesn't make the discovery any less genuinely unresolved. It simply means the mystery, for now, belongs to chemistry rather than biology, and chemistry mysteries in the outer solar system have a track record of taking years, sometimes decades, to fully untangle. There is at least a plan already in motion that could eventually settle the question directly. NASA's Dragonfly mission, a rotorcraft lander designed to fly across Titan's surface, is scheduled to launch no earlier than 2028 and is expected to arrive and begin exploring the moon's surface in 2034. Among its instruments is a spectrometer specifically designed to identify the chemical makeup of the ground beneath it, the kind of direct, close-up measurement no telescope, however powerful, can fully substitute for from more than 700 million miles away. If Dragonfly eventually flies over a patch of Titan carrying whatever material produces this signal, it may finally be able to tell scientists definitively what has been sitting in plain sight of Webb's cameras since 2026. You need to understand how unusual it is for two objects this different to share a chemical signature no one predicted in advance. Titan and Pluto formed in different regions of the solar system, under different conditions, orbiting different kinds of bodies entirely, one a moon locked to a gas giant, the other a solitary dwarf planet drifting through the Kuiper belt. For both to independently develop or independently preserve, the same unidentified surface material suggests whatever process created it may be more universal in the deep cold of the outer solar system than anyone previously assumed. The mystery isn't finished. Until either a laboratory experiment finds a compound that matches the signal precisely, or Dragonfly touches down and measures Titan's surface directly, the identity of whatever is absorbing light at 511 micrometers on two worlds separated by billions of miles will remain exactly what it is right now. A real, confirmed, thoroughly unexplained detail sitting in the data, waiting for someone to finally put a name to it. If you want to be there when that name finally gets attached, stay close. This mystery isn't finished yet.